Hello, can you hear my voice? Hear me? Hello. Hello, can you hear my voice? Yes, sir. Is it clear? Hello, can you hear my voice clearly? Please respond. If you can hear me, please respond. Now I'm going to share the screen. Okay, so can you see the screen, all of you? Can you see the screen? Hello. Please respond. If you can hear me, please respond. Hello. Hello, can you hear me? Okay, so in the last class we were discussing about the design of single reinforcement. Okay, and I think we have discussed about two problems here. The first one is explained. You saw the background. Hey, background noise is too loud. Okay, so can you hear me now? Okay, so in the last class we were discussing about example 6.1. Okay, so we'll just see the next one. Okay, I think example 6.3 was also discussed in the last class. Okay, so let us see the next one. It is very easy. Okay, so do you have any doubt regarding the last class? Anyone have any doubt regarding the last class? Do you have any doubt regarding the last class? Okay. So let us move to the next one. Yeah. See example 6.4. Okay, see example 6.4. Yeah. You just take one or two. Okay. So in example 6.4, you are asked to find out the design of beam for flexure. Okay, so first write down the given data. Okay, so next we have to find out the design moment because the load is given to you. Okay, UDL value is given, so the design moment will be 1.5 into WL square by 8. Okay. Okay, then you have got the design moment. Then we have to find out the limiting moment of resistance. Okay, so first we have to find out the value of RU. RU means this value. RU means this value. Okay, first we have to calculate this value because all the values are given. Xmax by D is 0.48 because in the question it is given that steel is Fe415. Okay, so after getting the value of RU, first we have to assume the value of B. Okay, width of the beam we have to assume first. So here in this problem we have assumed the value of width of the beam as 250 millimeter, and then we will calculate the effective depth required by this formula. Okay, so next after calculating here we will add this add the effective cover with this value to get the total depth of the beam. Okay, so therefore the size of the beam will be 250 into 580, which is our total depth. Okay, next we have to find out the area of steel. Yeah. So first we will find out the axiom x. Axiom x equal to 0.48 into d from this equation. So we have got the value of axiom x. Okay. Then we will calculate the area of steel by this equation. The actual equation was mu equal to this one 0.87 Fy AST into d minus 0.42 axiom x. Okay. So from this equation we have to find out the value of area of steel AST. Okay. Okay, so now after getting the area, what we have to do, we have to choose the diameter of bar. Okay, since you can see the area is higher here. Okay, it is around almost 2000 millimeters. So we will provide a higher diameter bar. So in this question they have assumed 25 millimeter bars. Okay. Okay, so then in the last class, as I told you, first after getting the area of steel, first we have to check whether we are getting the minimum amount of reinforcement or not. Okay, so this is the equation for checking that. Okay, from this equation we have got minimum area of steel is 276, but from our calculation we have got required area of steel is this much. That means it is more than the minimum value. Okay, that is okay. Okay, so if we provide 25 millimeter dia bar, so we can find out the number of bars. Okay, we can find out the number of bars by this formula, total area divided by area of one bar. Okay, so in this question we have got around 4 number of bars are required. So therefore finally we will provide 4 numbers of 25 millimeter dia bars. Okay, that is the conclusion for this problem. Okay. Okay, so now hope all of you understood this problem. This is a very simple problem actually. Hope you have understood the problem. Is it? Sujata, do you have any doubt in this? Do you have any doubt in this problem? Do you have any doubt in this problem, Sujata? Okay. Then Ishal, do you understand this problem? 6.4. Okay, so let us see the example 6.5. Okay, so you try to understand this 6.5 because this is the starting problem of this. In this problem, you have to use all the clauses. Okay, all the required clauses for designing a beam from 6.5. Okay, so you can see here design of example on design of singly reinforced beam for flexure as well as shear. That means here you have to find out first the area of steel, then we have to find out the shear reinforcement also. Okay, so this problem is going to be a lengthy one, so all of you try to understand. Okay, I will try to explain, and if you have any doubt after that you can ask me. Okay. So a rectangular reinforced beam is simply supported. Okay, it is given that it is simply supported and it is on 2 masonry walls. The thickness of the walls are given and the center to center distance is given 6 meter. And the beam is carrying an imposed load of, it is given, UDL value is given. Then it is also mentioned that design the beam with all the necessary checks. Okay, that means after designing the beam you have to check for deflection and also you have to design the shear reinforcement. Okay, so let us see the problem. Okay, so given LCC, that means L for length, CC means center to center. Okay, it is given 6 meter. Then imposed load is given, FCK, FY values are given. Okay, so here in this problem to start with, we will assume a total depth. Okay, so assuming a total depth of 500 millimeter. Okay, so how to assume that? You have to first find out this ratio. Okay, center to center distance divided by 12, L by 12 ratio. This value you find out, and then accordingly choose the value. Okay. Length is given, center to center length is given 6 meter, that means our 6000. If you divide the value by 12, you will get 500. Okay, so first we will assume the total depth of beam as 500. Okay, and then we will assume the width of the beam is 250 millimeter. Okay, so effective depth, therefore effective depth, what we have to do, again we have to assume effective cover for finding out the effective depth. Okay, so in this case we are assuming it is 50 millimeter. Okay, so therefore the effective depth will be total depth minus effective depth, effective cover, it will be your effective depth. Okay, so next, as I told you before, from I think clause number 22.2, yeah, from 22.2 you have to find out the effective span. Okay, for finding out the effective span we have to find out two values, center to center distance between the supports. So in this question it is directly given 6 meter, and then second value you have to find out is flare span plus d. Flare span will be 5.77, because you can see here 6 minus 0.23, because 0.23, how you have got this value, because the width of the support is given 230. Okay, so if you deduct this value from the effective span, you will get the clear span. Okay, so clear span plus effective depth was 0.45. Yeah, this one. Okay, so now you compare the two values, 6 meter and 6.22. So between these two values, this is the smaller one, so our effective span will be 6 meter. Okay, next we have to find out the self weight of the beam. Okay, self weight of the beam, this is the total depth of the beam, this 0.25 is the width of the beam, and this 25, it is our unit weight of RCC. You can see here unit weight of RCC is 25 kilonewton per meter cube. Okay, so if you multiply the value, if you calculate this value, you will get 3.125. Okay, then imposed load. Imposed load means, in other words, you can say live load is given. Okay, so live load is given. This is self weight, means it is your dead load. So live load plus dead load, it is your total load. Okay, if you have to add the two values. Then for getting the design load, you have to multiply the value by the load factor 1.5. Okay, so your design load will be this much. So therefore, the bending moment will be maximum bending moment or ultimate moment of resistance equal to WL square by 8. Okay, so you put the values here. W value is this one, L value is the effective span. Okay, so we will get the value of mu. Okay, mu means design moment. Okay, so after getting the design moment, what we have to do, we have to find out the minimum effective depth required. Okay, so for doing that, we have to first find out the value of RU. So in this case, your RU is 3.45. So then we have to calculate the D required by this formula, square root of mu divided by RU into B. So you put all the values. Okay, so after doing the calculation, we have got that the minimum effective depth required is this much. Okay, but in the starting of the problem, what we have assumed that the assumed effective depth is 450. Okay, so that means our assumption was correct. Okay, you can see here, since the depth of the section is okay, so this is the equation. The required depth is this much, and we have assumed this much. Okay, that means our assumption was correct. Hence, okay. Again, you can see here, since the depth of the section is more than the required for balance section, the section is an under-reinforced section. Okay. So under-reinforced section, therefore we will assume the adopted assumed value. Our total depth will become 500. Width will be this much. Okay. So now we have to see this. What is this? Can anyone tell me how we have got this value? Okay, for actual effective depth, we have to deduct these three values, okay, from the total depth of the beam, that is our 500. This is our clear cover. You can see here, assuming clear cover 20 millimeter. Clear cover minus 8. 8 means it is the diameter of stirrups. Okay, diameter of stirrups. Minus 20 by 2. That means 20 is the diameter of main bar. Okay, 20 is the diameter of main bar. Okay, 20 is the diameter of main bar. So we have to divide it by 2 to get up to the center of the reinforcement. Okay, so the actual effective depth required is provided is this much. 500 minus clear cover minus diameter of stirrups minus area half of the diameter of main bar. You can see here, it is written here. Okay, so next we have to find out the area of steel. Okay, so area of steel for an under info section, this equation you will get from IS 456 plus NX G. Okay, in this equation all the values are known except AST. So you put all the values and you solve it. Yeah. And if you solve the equation, you will get area of steel required is 833. Okay, so then what we have to do, we have to see the minimum area of steel by this equation. Just like the previous problem, we have to check the minimum area of steel. AS equal to 0.85 BD by FY. Okay, so we have got that the minimum area of steel required is 236 and we are providing 833. Okay, that means our design is correct. Therefore, we will provide, if we choose the diameter of bar as 20 millimeter, then number of bars we will get as this much, 3. Therefore, we require 3 number of 20 millimeter bars. Okay. Okay, so till this portion we have solved in the previous part. Okay, we have calculated the self weight, then design moment, then we have calculated the number of parts. Okay. Up to this part, it was our previous problem. In the previous problem also, we have solved till this part. Okay. So next, what we have to do? So here you have to provide 3 numbers of this much. Okay. Therefore, AST provided will be 3 into 314 means it is the area of 1 bar. Okay, it will be 942. Okay, so next, in this question, what it is given that after designing the beam, you have to check. Okay, here in the question it is mentioned that design the beam with all the necessary checks. That means you have to see whether the deflection is within the permissible limit or not, or whether the shear reinforcement is provided or not. These things you have to do. So let us see how to do the deflection. Okay, so now all of you open the IS 456 because for finding out this deflection you need IS 456. Okay, let me open IS 456 also. Yeah, control of deflection. This is clause number 23.2. Okay, now you see here, first you find out the percentage of steel. Okay, PT means percentage of steel. The formula is 100 AST by B into D. Okay, 100 AST by BD. 100 into this value is AST provided. Okay, not required. 100 into AST provided divided by B into D. Okay. So we have got that the percentage of steel is 0.8%. Okay. Next, this FS. What is this FS? You see in IS456. This FS is this means stress in steel. Okay. F for stress, S for steel. Stress in steel. Okay. So this is the formula to find out the value of FS. 0.58 Fy into area of cross section of steel required divided by area of steel cross section provided. Okay, so now because we have to use this graph, okay, so we find out the value stress in steel 0.58 into Fy is 415. Cross section of steel required, cross section of steel required is how much? It is 833. Okay, and provided is 942. So 0.58 into 415 into 833 divided by 942. Okay, so you will get the value of from this equation you find out the value of Fs. Okay, so if you use this formula you will get Fs equal to 212. Okay, 212. So now with these two values you have to find out the value of modification factor. This is KT from IS456. Okay, you see here we have got tension reinforcement is 0.8. Is it? We have got that percentage of steel is 0.8 and Fs value is how much we have got? We have got Fs equal to 212. Okay, 212. That means it will be between 119 and 240. Okay. So you see this line between 190 and 240. You will get one value here, somewhere here. Okay, 190 line is this one, 240 line is this one. Okay, so between 190 and 240 we need to find out 212. Okay, Fs equal to 212 we need to find out. Okay, so by interpolation you will get the value here, somewhere here. Okay, so here means it will be around 1.1 or 1.2. Yeah, it will be 1.29. Okay, this is the interpolation method by which we can find out. Okay, so modification vector we have got this much. Therefore, L by D max. Okay, this is the 20. 20 means for simply supported beam, the maximum value of L by D ratio is 20. It is given as per S456. See this table. For simply supported beam, L by D ratio is, it should be maximum value is 20. Okay, so L by D max equal to 20 into modification factor. That means K, 20 into K. K value is 1.29, this much. Okay, so next we will check what is the ratio of L by D provided. Okay, so L is 6000, that is the effective span. D is 462. So we have got the provided L by D ratio is 12.9. That means it is less than the maximum value. Okay, that means our design is okay. Okay, the provided L by D ratio must be less than the maximum value of L by D. Okay, so next, after doing the check for deflection, we have to design for shear. Okay, so this part we have solved in the previous chapter. Design of shear means we have to find out shear force, means design shear force, then nominal shear stress, then design shear strength of concrete. These things we have already done before. Okay, so I am not going to explain this part. Okay, because this has been solved in the previous chapter. Okay, if you can do this part. Okay, then we have to choose the diameter. Okay, okay. So next one thing means you have to check for development length. No, this part is not needed. Okay, development length part is not needed. It's okay. If you don't do this part, then also it's okay. It is not necessary. Okay, so design summary. And so in the design summary, what we will provide, what we will write, we will write the beam size. What is the size of the beam we have got? What are the main tension bars? Okay, it is 3 bars of 20 mm diameter. Then we will write down the shear stirrups. That means what is the diameter of stirrups? Okay, 8 mm diameter, 2-legged, 300 mm center to center. Then we will provide 2 numbers of 10 mm diameter bar anchor bars in the compression zone. Anchor bars equal to 2 numbers of 10 mm diameter bars. Okay, so this is the design summary. Okay, so now if you have any doubt in this problem, so you can ask me. Now, if anyone have any doubt, you can ask me now. Hello. If you have any doubt, you can ask me now. Okay. If you are not asking anything, that means you have understood everything. Okay. Okay, so I will share the PDF with you. Okay. I'm going to share the PDF in your group. Okay. So you please go through the PDF, and if you have any doubt, you can ask me in the next class. Okay. So thank you everyone. Thank you everyone for attending to this class. Okay. Thank you.